Who among us would like to take a dip in the fountain of eternal youth? Probably all of us would. The thing is that today, this is a reachable reality. However, we need some time. That is why we need cryopreservation. The problem with cryopreservation is the presence of ice. So there are two strategies to avoid it. One is to use a cryoprotectant, a molecule that you put in between the water molecules and avoid them to stick together. The second one is to have a very fast cooling and even more faster rewarming. Historically, the solution or the choice has been the electromagnetic radiation. First with microwaves, then with what is called nanowarming, and more recently with the electric heating. They are all wonderful technologies with impressive good results and promising results. They all share this capability of penetration, of heating inside. That is what you need in order to have a quick warming rate. However, they also share some drawbacks. First, the thermal runaways. Second, they cannot be monitored by medical image. You cannot put metallic parts inside an MRI or a CT. And finally, in the case of nanoparticles, the nanoparticles should have been put before the cooling. So there are hundreds of samples in the banks that has been cryopreserved without the nanoparticles. So welcome to the future. I think that the future is ultrasound. In ultrasound, what you have is thousands of transducers, each of being sent a beam of sound to the point that you want to hit, and you do it with a precision of micrometers. And you do it because each transducer is steerable. You decide where to shoot the beam. And you do it in real time. All the process is controlled by MRI. So, for example, in this case, this patient with essential tremor recovered the capability of writing in question of minutes. The applications of this warming with ultrasound in medicine are hundreds. Even that's not fit in one single screen, but there is still some room for something else that I think it could be cryopreservation. I started thinking this idea something like 20 years ago, but it was not till the cryo meeting 5 years ago that I decided to publish the results. From my point of view, at that point they were enough reliable. It was the heating of a ovary, a whole ovary, of a woman ovary, with only 23 transducers. And you see there, I don't know if the pointer works, this region represent the homogeneity of the heating, and these tight lines that are ascending represent how quick the warming is. So something like 200 degrees per minute, that is more than what you need. After that, then I was convinced myself, so I decided to build the setup, is this one, and to look at the performance. On the left, you have the cooling curve, and on the right, you have the warming curve. You see that it is almost instantaneous. And afterwards, I decided to test in 3 different biological samples. First, aortic rings. So they contract after the rewarming with ultrasound, not as the conventional way of preserving that are only tubes that you need to replace after some time. They are alive. As I said, they contract. And also the inner extractor is perfect, even at electron microscopy where you do not see any fracture, contrary to the standard procedure. The second example was something more challenging. It was the case of adult C. elegans. The adult state of the worm cannot be cryopreserved. The recovery rate is 0% practically. But as you see here, from 0% on the left, just by raising the time of exposition to the ultrasound, you get almost 100%, or worms alive. Or just by increasing the power of the ultrasound, you also get from 0%, that is the standard recovery rate of the adult C. elegans, you got something like 100%. These are two movies of two words moving, but it doesn't work in this computer. And finally, it was published only a few months ago. It was, we decided to go to a transplantable organ. In this case, it was a mouse heart. We were able to publish in this gold standard journal of transplantation, in which we take the heart and put in deep hypothermia. On the left, this vertical line is the recovery with the ultrasound, and the performance is, as you can see, around 100%. But instead, if you recover in the standard procedure, that is 5 degrees per minute, the recovery rate due to this sensitivity to the second word ischemia of the mouse heart, practically they don't beat at all. So the internal structure is perfect, and also this is one of these hearts beating after the recovery with the ultrasound from deep hypothermia. So the markets, now people talking about investors, the markets for ultrasound reanimation moves billions probably, of course, organ transplantation, but also the case of fertility preservation, in the case of ovarian tissue, that is a very growing and rapid field. In the case of tumor banking, solid tumor banking for testing drugs, for example, or correlation with secondary tumors, or studying metabolic path. In the case of gene and cell therapy, where there are tough logistic problems in this field, that ultrasound can say something, the preservation of biodiversity, of course, and of course, also human cryopreservation. So these are our facilities, and this is the more important part, that the students that are doing, they are very enthusiastic about these ideas and doing the tough job in my lab. They are all wonderful guys. And nothing, this is the last slide. I wanted to show you the fingerprint of the ultrasound wave fighting against the ice that was put in liquid nitrogen. This whole was done by the ultrasound fighting against this piece of ice that was in the tank. And as Feynman said, nothing tells that death is not inevitable at all. Thank you very much. This is my talk. Thank you very much.
Thank you. Any questions? Maybe time for one question.
What the medium of transport is? Are you like placing electrodes on the person's head? Do you have to, you know, like basically physically, like how are the transducers attached to the thing being warmed?
All right. In the case of always, the sound propagates in something like a liquid. Mm-hmm. So it needs to be covered by a liquid or a gel, something like that. In the experiments that I did, it was ethylene glycol that was cold enough to keep the sample cold, but allows the
immersed in the ethylene glycol.
Exactly.
Are then in the solution, and then
right, and then the beam of sound travels in this liquid till they reach the point that you want to warm. This in liquids. Thank you very much. This
cool.
is my talk.
It's very cool.
Thank you.
Very cool new approach.
Thank you very much.